is Udit, and in today's video I'll be discussing on this topic, this question, searching an element in a sorted and rotated array. So here you can see that this array is not a sorted one, but rather it's sorted and rotated. So to understand this concept of sorted and rotated, you consider that this array initially was something like 1, 2, 3, 4, 5. Okay, so what happened is that I have rotated this array by the index of 2. It means this will go here, this will go here, this will go here, this will go here, and obviously this will go here. So by this rotation of one step, I can get an array which is of something like 2, 3, 4, 5, 1. Okay, now again what I'm doing is like as per this given array, I will again rotate this array. So this is going to come here, this is going to come here, this is going to come here, and so and so. So at the last, you will generate an array which is sorted, but it is rotated. So in the given question, the question is that we have to find an element or find a value in a sorted rotated array, but the fact is that in logarithmic time. So the algorithm complexity is going to be order of log n. So this is challenge because if you're given some array and you are being told to find the element 1, then it can be easily find out using linear search algorithms which is of order n. I'm just going to iterate the loop from this point to that point, and I'm going to get somewhere it's going to be there, or maybe if it's not going to be there, in the worst case we have the big O n. Okay, alright. So as per given problem, we have been asked to search an element using an algorithm which has big O of log n. So my target is big O of log n. Now if we take this example into consideration, so I suppose if I have the array 5, 6, 7, 8, 9, 10, 1, 2, and 3. So this is the given array, and you have been told to find out at which point, at which index this value 3 is existing. And if the element is not there, you just have to simply print out not found. If it is found, then you have to print the index. Now, since the question has been asked to find out the logarithmic searching algorithm, so the first thing which is going to for sure come to your mind is that the algorithm which is logarithmic and it's a searching algorithm is none other than binary search, because we know that the binary search order is log n. Okay, so we have to basically do binary search in this array to find out this element. So but here you can see a fact is that for a binary search, the prerequisite for a binary search is that the array must be sorted. Okay, so if it was 1, 2, 3, 4, 5, 6, 7, 8, 9, then I could have simply applied binary searching. But since the array is not completely sorted, rather it's rotated and sorted, so I need to find out a way to tackle this problem. So from here I can figure out, or you can state that 5, 6, 7, 8, 9, 10, 1, 2, 3. Now from here you can figure out is that if I'm moving from here and I'm continuing to move, I can see till this point. Okay, so try to imagine till this point in array, the numbers are in increasing order. Okay, and just after here, though it is increasing order, but here it's a break, means here it should be 11, 12 and 13, rather it's 10, then it's 1, and 1 is actually less than 10. So from here I can figure out is that I can actually separate this array, this given array. What I'm going to basically do is that I have not written code of this problem yet, so I'm just doing a kind of live coding so that you can understand how I approach the problem and solve it. So here I can find out is that from this point to this point, and from this point to this point. So from this, if I consider if this is a whole as I treat as an array, then this is a sub array 1 and this is a sub array 2. This one is a sub array 2 and this one is a subarray 1. Now the binary search prerequisite is that the array must be sorted to perform binary search algorithm. Now here we can see if we can divide the array into two parts such that both of the parts are sorted. We can apply uh, on both we can apply binary search algorithm. On both part we can apply binary search algorithm to actually find out whether uh, the element is existing or not. Okay, so yeah, this is pretty good. So at this point I can state is that now I can state that my goal is to find the breakpoint. Okay, so now my goal is to find the breakpoint, and what I mean by breakpoint means change in pattern. Here you can see the numbers given by the users as it is in increasing order, right? Here it is increasing, here it is increasing, here it is increasing, here it is increasing, here it is increasing. The moment I come into this place, I see a breakpoint. Okay, so I'm going to call this thing as pivot. Okay, for instance, I'm going to tell it as pivot. Okay, so this is a pivot point, the point from where I can actually divide the array into two parts and perform the binary search algorithm. Okay, so that my total big O of algorithm is order of log n. Now, okay, so apart from before coding, actually I can try to find out how I'm going to put the condition. So the condition is going to be something like once I've got the pivot point. So once I have the pivot point, I know where the pivot point is. So what I can do is that okay, so let's say the element which you're going to find, the name is key. Okay, so key is the element which you will have to find, or you need to find inside this array. So what you're going to do is that the condition is going to be, the first is going to be if let's say this array name is ARR. If ARR pivot is equals to key, then I'm going to simply return the pivot. Okay, and again I will have else if. Okay, so in else if, what I'm going to do is that if the I can tell is that if array n is the size of array n minus 1, if I can do it, if it is greater okay, so if okay, so I can actually do this thing. So I'm just rubbing off this condition because give you an idea. Okay, so else if, so that condition was there, it added this condition is that if my key is greater than array n minus 1, where n is the size, and the reason I'm doing n minus 1 is that because in the array index starts from 0. Okay, so basically what I'm doing is, suppose you need to find out, suppose for example if key is equals to say 8. Okay, so if 8 is greater than this last element, then I can for sure tell that my value which I need to find will be somewhere in the subarray 1, right? So if the key element, the element which you need to find, is greater than the last element of the array, then for sure it means that the key is going to be into this subarray 1. Alright, so I will call the binary search, basically I will call the binary search from index 0 to this pivot index. Oh, oops. My handwriting is very terrible. Okay, so I'm going to call the binary search algorithm from 0 to pivot minus 1. Why I'm doing pivot minus 1? Because pivot, I've checked for the pivot condition, I've already checked that condition just before that. If array pivot is equals to key, so suddenly the array will, the element will be, the probability is that the value will be somewhere from 0 to pivot minus 1. Else if, oh, okay, I don't need to put else. Else is also going to work. Else, I mean, if the remaining part, then obviously the element is in this part of array. Okay, like for example, I'm going to give you an example just to give or consolidate my point. Say if key is equals to 2. Okay, now what we know is that is 2 greater than 3? Nope. The condition is false. So that means the search is going to be in this sub array 2. So this is all I can tell you is that. So now let's just start coding. And I'm going to have the main function. And in the main function, I'm going to declare this variable size, a key of pivot result index. All right. So this is going to be the all variables value we'll be using. If I need something extra, I will surely put it up there. So size is basically going to store the size of the array. The key is going to store the element which I need to find. The pivot is the element which I will be using to store the breakpoint or the point from where the pattern is changing. As you can see, if you remember, here I'm showing you. Yeah, so you can see the pivot point at this is this part. So this is the pivot point. So the pivot variable is going to store this index where there is a change in pattern. Okay, so that I can call the binary search algorithm for the both subarrays. Okay, now so the next thing is I'm going to take input into the size and the key. Okay, and then I'm going to store it in. Okay, so it's ARR as I said you. Okay, now the thing is that what I'm actually planning to do is that I will be checking for the pivot point while user is entering the data. Okay, so while the user is putting the data, I'll be analyzing the change in pattern. Okay, so for this what I will be doing is that I will be explaining to you this shortly. Okay, it's ARR. Okay, I don't know why I have this habit of using array as ARR. Okay, so if RR greater than ARR I minus 1, pivot equals to I. Okay, alright. So here what you can do, see is that what I am doing is that first of all I am taking the first element out of the loop, and the reason for doing that is that I'll be doing something called as checking. Okay, so what I'll be doing, for example, I'm going to take you back to the example. What I'm basically doing is that for the given number by the user, I'm going to check if the previous value given by the user is greater than the given value or not. Okay, so basically what I'm doing is that, let me take you through the example. So here I have this example. Let me clear out. I'm not clearing out because this is going to create a lot of problem. So yeah, so consider, yeah, yeah. So let's say we have something called as 4, 5, 6, 7, 8, 1, 2. Okay, so what I'm doing is that first of all I will be running a loop from int. Okay, so I guess I need to change my loop condition. Probably it's 0, so it's going to start with 1. Okay, sorry. So here you go. So I have basically, so the index is 0, 1, 2, 3, 4, 5, 6. Okay, so what I'm doing is that this value, I'm taking this value outside the loop, and the reason is when I am taking input for this value, I'm checking whether this value is greater than this or not. If the condition is true, then only if the condition is true, then I'm doing nothing. If the condition become false, I store it as a breakpoint, or you can say the pivot point. Okay, so from, if you take a look at the code so far I've done, which I've done here, you can see I've written if ARRI, if ARRI is less than ARRI minus 1. Okay, right? So here what I'm doing basically is that I'm looking for checking the condition is that if ARRI is less than ARR I minus 1. If the condition is true, then I store the ith index as the pivot point. It means it's a breaking point. Okay, this point, I mean this point. So let us just dry run this statement so that you can guess what is happening actually. So by the way, I is starting from 1 and it is lasting to 0. The n means less than n, means I is less than 7. Alright, the size of the array is 7. Okay, so when here you can see that ARR1, this condition I minus 1 is 0. So you can see that ARR0, I'm substituting value of I is equals to 1 here. So I'm getting this thing. So is ARR1 means this index, the value at this index is less than the value before? The answer is no. So I don't do anything. So let me substitute I is equals to 5 for I is equals to 5. So I'm going to get this kind of equation. 5 minus 1 is 4. Okay. So is ARR4 greater than ARR5? AR4 it is 8 and 8 is greater than 1. The condition is true. Since the condition is true, I'm going to store this ith index as the pivot. So from here, I can tell you is that we have solved almost 50% of our question, which is finding the pivot point. Now what I need to simply do is that I need to call, according to the condition given, I need to call the binary search algorithm. That's all what I need to do. So now this question becomes pretty simple. Like, yeah, pretty simple. Okay, so now I'm going to do something called as condition checking. So if the current pivot point is equals to key, I'm just checking. If it is yes, then I'm going to store it in a variable called as result index is equals to pivot. Else, if the key is greater than array size minus 1, for result index, I'm going to basically call the binary search algorithm, which I have not defined so far. This I'm just writing it. Binary search algorithm. Okay. So just to give you what I can do is that, so I need a password. So let me just create this function. In the binary search. Okay. So the binary search is going to basically take formal arguments as int. It's an array. Then it's going to take the start index from where he needs to start and end the search. I mean the range of search, and then obviously a find, which is going to store the element which we need to find inside this array. Okay, so let me just pass this. Okay, now let us discuss this condition. Means I've discussed, but let us see how we're going to do this. So the condition is else if key is greater than a size minus 1. Okay, so this has popped up. Okay, yep. If key is greater than size minus 1. So as I said you in this statement, okay, let me just take you to that same problem. Did it somewhere here? Did I? Alright, so let me just do it again. So I have this 7, 8, 9, 1, 2. I'm taking a pretty small example. Okay, so just to make you understand this thing. So suppose I need to now from the so far we know is that this point is the pivot point, right? This point is the pivot point. So 0, 1, 2, 3, 4, 5. So the pivot point or the pivot index is currently 3. Okay. Now the key suppose is say 9. Okay, for example it is 9. Now what we know is that ARR, we are checking for the first condition, the very first condition is array at pivot index is equals to key. Now here at array pivot it is 1 and 1 is not equals to 9. So this condition is false. Then it's going to check for the other statement, the other else if but, which state that is, I'm just going to show you that condition. Okay, so this one is key greater than a size minus 1. A size minus 1 is basically the last element of the array. So I'm checking whether the key is, so the is key is greater than last element. This was the first condition, this was the second condition, last element. Now key is 9 and the last element is 3, right? So we know 9 is greater than 3, the condition is valid. So what we know is that since 9 is greater than 3, what we know is that my element will be somewhere in this part. Okay, so I need to call the binary search algorithm for index 0 to pivot minus 1. Okay, so index 0 to pivot minus 1 I'm going to call. So I'm going to write, so first let me check the pattern here. So I'm first taking, so first I'm passing the array, then I am passing the starting point. Oops. The starting point which is 0, and then I'm passing endpoint which is pivot minus 1, and then I'm passing the value which I need to find, which is key. Okay, seems good. I don't know why I keep using a for array. I have this habit of doing this every time. I don't know why. Okay, so all right. Now I'm going to go for the second. Now I'm going to show you the second, third condition. What if the pivot? So I'm just going to rub off this without. Okay, I'm just doing side this point. Okay, so we have 7, 8, 9, 1, 2, 3. This is very light. I need to fix this. I'm taking a minute. So 7, 8, 9, 1, 2, 3. 0, 1, 2, 3, 4, 5. Okay. Now, suppose the key element, the key is 2, for example. Now, what I'm doing is, now if this condition, if we apply this condition, which is key, is key greater than the last element, the key is 2 and the last element is 3. So is this greater? The condition is false. So what I know from this part is that my search is going to be limited to the sub array 2, which is from pivot plus 1, this point is pivot as said earlier, pivot plus 1 to the size minus 1, because we are counting from 0, right? So size minus 1. So let me just apply this line here. So what we did have was pivot plus 1 as my starting point, and it was, the search was going on till size minus 1. If I'm right, this is okay, I guess. Now I'm just going to simply define my binary search algorithm and print the values. That's all what I need to do. Pretty simple. So the binary search, if you don't know binary search algorithm, I highly recommend you to get an idea of it, because I'll be doing simply applying it without giving much overview into how it is actually working. Because this video has gone up to 20 minutes plus, so I'd encourage you to first see what binary search algorithm is if you don't know. So first of all, we need to check the condition if n is greater than or equals to start. Alright, so this basically means that if my n position is greater than start or not, if this condition becomes false, then that means that we have searched the entire array but we have not found the element, and in that case I'm going to return -1, which is going to be a symbol that we did not found the value inside the array. So in the binary search, we all know that we find the middle position using this simple thing, which is start plus end minus start by 2. We find the midpoint. If a at mid is equals to find the element I'm finding is actually right in the middle position, then I will just simply return mid. The integer type is integer. Okay, cool. So else, if I'm going to check if the a mid is greater than find, then I'm going to do the binary search. As you all know, since the a mid is greater than a mid is greater than the value which I need to find, then the search is in the left half of the sub array. mid minus 1 minus fine. So I'm just passing if I'm doing it correct way. Yes, looks good. Else to some return binary search take on my mid plus 1 comma end find. Alright, seems good so far. So what basically here I'm doing is that if the value which I'm finding is less than the value by the middle, then I search for the left part. If it is not, then I search for the right half of the sub-array. So I highly encourage you to go through this binary search algorithm if you don't know. You first need to understand this algorithm before applying it. So if my this condition become false, that is the n becomes less than start, that probably means that the array indexes, the end and the start have crossed each other, and so we are that means that we have searched the entire array but the element was not there inside. So here I am getting a warning which is variable index set not used. Oh yeah, so I just need to, so far what we have done is that we have searched everywhere and everything is done. Now we just need to simply print out the value. So if result index is equals to -1, that means I've searched the entire array but I did not found the element. So I'm going to print out element not found. Alright. Else I'm going to do cout element found at index result index. Alright, so far good. And at the end you need to do this thing, return 0. It's a good practice to do this. Okay, so far everything looks fine and pretty good. I'm impressed. So let me first take back to this point and just run it with some sample code. So I'm just going to provide the sample code given here, and obviously I will be doing some edge cases testing. So here you can see that the size of array is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9, and the element I need to find out is 3. So then the answer is going to be 8 if I put into this order. So let me just do this. Yep. Hit run. And this is going to probably work. Let's see. Okay, so it was 9, right? So the way I was taking the input was I was taking the size. Okay, so the size is 9 and the thing which I need to find is the element which I need to find is 3. So first I'm going to give what was that? Okay, so 5, 6, 7, 8, 9, 10, 1 to 3. 5, 6, 7, 8, 9, 10, 1 to 3. Okay, so I'm going to feed 5, 6, 7, 8, 9, 10, 1, 2, 3. So yep, I got the right answer, which is element found at the index 8. Good, but let us do some edge case testing. That is element is not there in the array, like returning -1. So for this I will be, let's say the size of the array is 7 and the element I need to find out is 56, and I will be putting this some random values. So let's start with 8, 7, 6, 5, 4. So 1, 2, 3, 4, 5 and 1, 2, 1, 2, 3, 4, 57. Okay, so we got element not found because 56 does not exist in this array. So far code is working very fine. So let me do this another edge case testing, which is I'm going to take some size, let's say 8, and the element I need to find out is 2, but there will be a repetition in values. So what I'm going to get here is something interesting, I guess. 1, 2, 3, 4, 5 and 3, 8. Alright. So yeah, it is giving me the correct answer, which is element found at the index 6, which is 2. So far our code has worked very well and it's giving the correct output. And we have solved this problem, which is from this website GeeksForGeeks, that we need to develop an algorithm which is going to give me the answer in order LogN. The question inside will be probably coming inside you is that why are we actually performing LogN algorithms? Okay, So we have we can just simply perform linear search and we can do it. It's order n. Okay. So to explain you that why in future you need to be efficient, you just not need to find a solution to a problem. You need to be efficient in your algorithm, and that's why today I have picked this question specially to make you understand what is the role of efficiency in terms of real life programming. So here you can see I plotted this two graph, which the green color represent the order of n, which is x order n algorithms, and this red one graph represent my log base 2x, means logarithmic algorithm. So basically this is the algorithm for like binary search, and the the algorithm which we have written right now, it falls under this criteria logarithmic, and this is order n, which is going to be linear search. So let me show you what is going to be the difference. Consider the value on the x-axis is the size of input, and the value on the y-axis is the amount of resources your algorithm is going to consume. And we all know bigger notation does not tell you how fast your algorithm is, but rather it tells that how your algorithm is going to behave with increasing number of input size. So since our axis represent the input size, we can see that as the x value is increasing, we are moving from this origin towards the positive x-axis. The y-axis in logarithmic is taking a bit less turn rather in this thing. This thing is going up and up and up. Like for example, let us consider, I'm going to take a big number to show you the difference. Suppose if my array size is 250, you have taken array size of 250. Okay, so if we take array size of 250, then the algorithm which we have written right now is going to approximately take 8 seconds to execute. Now please don't compare it with the result which you will be getting. The result will be different, but it just give you a kind of visualization that how this algorithm is going to behave with an increase in input size. So if I take a array of size 250, it's going to take nearly 8 seconds to execute. 8 seconds. And on the other hand, if we do it using linear search algorithm, it's going to take 250 seconds. So you can feel the difference, 8 seconds versus 250 seconds. So this is the importance of doing algorithm in efficient form, and this is highly useful, and I highly encourage you to solve this problem and do it on your own. If you have any question, any queries regarding this problem, you can know me in the comment section down below. Thank you for watching this video.